Today's guest is Philip Weiss, Vice President of Software Engineering at Orbital Sidekick. They're a customer of AWS Aerospace and Satellite, and we discussed how AWS infrastructure enhances their missions.
My name is Philip Weiss. I'm the Vice President of Software Engineering at Orbital Sidekick. What OSK does is we have a constellation of 5 hyperspectral satellites, and what hyperspectral cameras are is think of like a normal photo kind of gets split into its components of red, green, and blue. Our satellites split the spectrum from ultraviolet all the way up to infrared into about 470 different spectral bands or colors. And then we use that information to look for things. Our main customer base is oil and gas industry. An oil pipeline company needs to know when they have leaks. Methane or oil leaking reflects light slightly differently than the surrounding things. Just like water reflects blue, when you're looking at it in 470 different spectral bands, methane reflects in color. And we use that to be able to tell when our customers have leaks. Outside of oil and gas, we can look at vegetation health. We can tell when vegetation is healthy, when it's not. We can look for specific minerals. Just was chatting with a potential customer about looking for specific kinds of rocks. If they are spectrally significant, we can see that as long as there's no clouds. So that's what we do.
Wow. So there's the making things more visible, but also making things that you can't see visible, sort of in a manner of speaking. That's got to be a fascinating intersection of not just what space data can provide, but also these different industries. Like you mentioned, the energy industry. As many industries are controlling emissions and decarbonizing, that's got to be a fantastic place to be right now.
Yeah, at scale from space, we can be able to see things that are a lot harder to see or a lot more expensive to see from the ground or locally. So if you have an oil and gas pipeline that runs through very remote areas or a mountainous area that is hard to traverse, that's not difficult for us to see from space, like I said, as long as there's no clouds. And we can dig out things that could cause major problems. I don't remember exactly how many years ago it was, but there was an oil pipeline or a gas pipeline that exploded on the edge of a city in Washington State and caused a lot of damage. And we would very much like to not have that sort of stuff. We'd like to be able to help make the carbon that we still have, at least, a lot safer, for one. Or just even cut down on the amount of carbon emissions that from the remaining carbon that's out there so that it isn't being emitted on there. We have a leak that's going out there. If we can detect it months before it'll be found at the next traversal of their pipeline, that is a very interesting thing for us.
We must be talking about an unbelievable amount of image data, given it sounds like the images are being refreshed rather quickly. This has got to be a lot of data.
Yeah, so that's actually one of the things where AWS comes in is a huge benefit to us. If you think of a normal image, number of megapixels is what, people think of when you're taking with a camera. Ours, because we're splitting this up into so many more bands, the images get really, really large. A typical image for us will be 4,000 pixels by maybe 1,000 pixels. I don't know the exact numbers on there, and it varies depending on how we collect it. But for each of those pixels, there are 470 values that we have to collect. So those files, when we drop them in, are huge. And so being able to store those efficiently, being able to quickly process them, the amount of data is quite immense. And it's, unlike the stuff where I've worked on before, where you just have massive numbers of transactions, we don't have massive numbers of transactions, but the amount of data that we have to pour through is still large.
What kind of file sizes are we talking about?
From 100 megabytes at the small end of it on there to once things are fully processed, we can get things up to 10 gigabytes sometimes, which is very, very, very difficult to process through quickly. And one of the reasons like why we choose to do this with cloud provider is that trying to grind through that on a, even a pretty powerful single machine that sits in a closet somewhere is slow because those can only do so much at a time. With AWS, we can just spin up all sorts of compute resources and work on specific bands at a time, multiple images at a time, particular areas of images at a time, and we can have multiple pieces of that spread out across all sorts of compute.
Okay, a 10 gigabyte file. As I said, that's a hefty image. If that's on the regular, how are you extracting meaningful insights from that in a way that's not taking you all forever?
So the basic idea for how this works is that a few times a day, our satellites will drop information to us whenever they're over a ground station that we can use. And they drop as many files as they can during a short period. We literally trigger this as soon as a file shows up in AWS S3. And what we can do is for each of those files, we start a processing pipeline. We use AWS step functions for those. And for each file, we'll literally go through a number of functions within step functions. So we will locate where the image is. So it's not as trivial as I would have thought when I first started this image. It's not just, magically right there. You have to find out specifically where it is. You have to do what's called spectral calibration for those files. We don't just have 3 colors to do it for. We have to do it for 470. Huge amounts of stuff that you have to go through correcting all of this. Another step that we will then have to do is something called georeferencing and orthorectification for the data. So that is taking into account elevation. That can be extremely time consuming because you have to actually get an elevation map for the entire area that your image covers. Then we have to calculate a whole bunch of other things. For instance, the actual methane map that we normally do, the oil map that we do, or a cloud cover map. Can we figure out where the clouds are and not use the portions of the image where there are clouds over it? Or do additional processing. So when we do cloud cover on there, we have both parts where there's clouds and then parts below the clouds that are covered by shadow. And what extra processing do we have to do for shadowed areas in order to bring out the information that we need to do? I should note our sensors are not active sensors. These are not like radar where they send out a signal and we calculate the amount of time it takes to come back or something like that. These are entirely passive sensors, kind of like a normal camera is. So you're looking at that dark spot on your normal camera image on there, if you change your white balance or all the other things on there, you can still see things with those. So when we have shadowed areas, we can do additional stuff with that and be able to see things.
I'm just trying to imagine taking on this kind of compute. If you were trying to home grow this, would that even be possible?
It can be done on your local computers. You don't want to. So, for instance, when I started, we had the folks that were at the company previous had built out some experimental compute pipelines using a very, very beefy machine, and I don't even know what the hardware that went into it, that sits in a closet in our office. And when we got imagery, in this case, it was not from space, it was from aerial flights with the same kinds of sensors. The time that it would take to process all that, you would start it at 9 o'clock at night, and you would come in the next morning and it would be halfway done. on there.
If it didn't fail halfway through, right? Or
If
something.
it didn't fail halfway through or for parts of it on there, just because you have to grind it. And this is where we get into something like cloud. However many files you have, there's probably a practical limit to how much compute AWS actually has. But we're coming nowhere close to actually hitting that. If we want, we've got 50 files on this, and we want to do them all at the same time so that they finish in about 20 minutes, which is more or less what it takes for us to process each file right now. We can do them all at the same time on there. And it doesn't actually cost us any more than if we did them, one after the other on there, because we use Lambda functions for the actual compute processing. Occasionally, we may run into limits for how many we can do at once with that, but so far we haven't really hit any kind of limitations like that. And because of that, we can get, whenever we get image drops, the record so far I've seen from image acquisition on the satellites to when it's processed, the fastest I've seen so far with what we've been able to do is about 34 minutes. That includes transmission time, delivery into an AWS bucket, and then for the processing to go through.
You blew my mind a little bit. Sorry, that's so fast. You went from hours to minutes. That's crazy.
It was a very opportune data collection. The image itself was taken just before we hit a downlink window. And so the image was taken, and then it was almost immediately downlinked, then transferred into an AWS bucket. And from that triggered this, and I'm like, when I saw the numbers on there, I was like, wow, that was very, very fortuitous. However, one of the things that we will be doing on there is being able to prioritize certain pieces of data. So, if we do some compute on board, we'll be able to tell, here's an image where we think there is a very high probability methane leak. We will be able to, at the next downlink opportunity, which generally happens about every 90 minutes right now, as we get more downlink stations with capable radios, those will come up a lot more frequently. We can downlink the data, process it, and get that insight out to our customers. So there is no one that has to push any buttons for any of this to happen, either at AWS or on our end. Now, and that's also very different from when this pipeline that ran on a computer processed. For that one, and some of that we couldn't have done completely automatically because we had to collect the hard drives off a plane, and somebody literally had to physically carry those into a place where we could uplink them. And I got to say, a lot of oil pipelines are not in places with great internet. So
often quite remote, right? Yeah.
So trying to get some of that uplinked on there. Coming from space, we have, in many cases, have better internet than we would driving around in the Texas high country, where you got to find a place to uplink it. Someone had to push a button to run it. Someone had to look it over. Someone had to figure out just how much can this machine process at a time on there, and then split it up into chunks so that it could run on there. We don't have to think about that. We launched satellites 4 and 5 in March. All we had to do was update a couple of database entries to mark down the IDs of the satellites, so we can recognize that these go in there. And everything on the AWS end, nothing had to be done on that end afterwards. Just put a couple new database entries in, and it literally just starts spinning up. We don't have to say, give us more compute specifically. They just give it to us when we want it. So,
wow. Okay, you all still have some of the first data that you ever downloaded from your satellites. You've now gone back and reprocessed them with AWS?
There literally is almost no data that's wasted in what we do. Some things may be somewhat less useful than others, but we can look for all sorts of things. it might be a little bit late for a methane leak on there to process, 6-month-old data or 3-month-old data, but we can still tell, for instance, things like crop health during that period. The data is always good for that particular time. So if you come up with something else that you want to look for, now we can do that, for instance. And if that mineral is something that you can see spectrally, we can go back and look through all of our imagery and reprocess that with a particular algorithm to say, oh, maybe go find that around last year. Look for new sources of a particular mineral, or what your crop health was at a particular time, or we're doing research on speciation. So what's the makeup of a particular forest on there? Is it, we can go back and look at old data for that.